Okay, this is Chapter 6, Work in Kinetic Energy, and everything that we've done up to this point, we've been using Newton's second law and forces to calculate accelerations and velocities and positions and so on and so forth. Now what we're going to do is we're going to take a look at forces in a little bit different light and calculate how much work is done by a force. Work is related to giving something energy, so we're going to talk about two types of energy in this chapter. We're going to talk about kinetic energy, the energy of moving things, and we're also going to talk a little bit about springs and their energies. Work and energy are related. We're going to talk about how they're related and how we can actually use this to solve physics problems. And last but not least, we're going to take a look at power and how that's related to energy. So it turns out that everything that we've learned about forces using Newton's laws was excellent. However, Newton's laws become extremely complicated when the forces are not constant. If the forces are not constant, then we know that the acceleration is not going to be equal to a constant, and motion becomes much more complicated. However, we can get around this using the concepts of work, energy, and probably the most important idea, which is the conservation of energy. We can use these concepts to deal with problems where perhaps the force is not constant. So let's talk about what work is. It turns out that if you apply a force to a body, then you've also done work to it. The caveat is that the body needs to undergo a displacement. Displacement being a vector quantity. So, if you think about, if I go out and I run around the track, and I start right here, I've gone all the way around the track, I'm applying a force, to the ground's applying a force back to me, and I end up at the starting line, then my displacement is actually equal to 0. Therefore, I've done no work. Thinking about the simplest possible case, however, if we are pushing our car up a hill because we ran out of gas or something like that, or if we take a box and we apply a force to it, and the box does undergo a displacement, here displacement is here over in this direction, then we can simply write that the work is equal to the force multiplied by the displacement. I'll say that this is the simplest possible case, and this isn't always true, as you'll see on the next slide. Something to also think about is going to be the units of work. If work is equal to the force multiplied by the displacement, we know that the units of force is equal to a Newton, and the units of displacement is going to be equal to a meter. That says that the units of work is going to be a Newton meter, and this actually has a special unit, or a special name. This is going to be called 1 joule, written with a capital J. I'll also talk about energy here in a little bit, and the units of energy are also going to be in joules. Unfortunately, the simple example from the last page doesn't pan out if the force and direction, or displacement vector, are not in the same direction. We simply cannot write work is equal to force multiplied by the displacement. Not when the force and displacement are in opposite directions, so we can't do that. What we really want to do when we talk about forces is we want to say that the work is equal to the force dotted with the displacement. Remember from chapter 1, this is a dot product or a scalar product, and what that's really saying is how much of the force is in the same direction as the displacement. That is how much work you've done. So the definition of this was the magnitude of the force multiplied by the magnitude of the displacement, or multiplied by the cosine of the angle in between them. That's a phi. So we would write our work as the slide has right here, where we no longer have the vector signs on top there. These are just magnitudes. And again, what that's kind of doing is that's saying I'm going to take my force right here and I'm going to break that up into two components, a parallel component, which is going to be the force multiplied by the cosine of the angle right there, into a perpendicular component right there. Now, this perpendicular component is not in the same direction as the direction of motion. It has no component in the direction of motion. The direction of motion is this direction right here. So this perpendicular component is going to do no work on the car. All of the work that was done on the car is in the parallel direction, the same direction as the displacement. And now we simply say, okay, this is the parallel component of the work, so the force multiplied by the cosine of the angle in between them multiplied by the displacement s. You can also do this using vector addition, and take a look at the first chapter to refresh your memory on how to do that. This angle leads to the idea that this force can do positive, negative, or zero work, really depending on the angle between the force and the displacement. So we're taking a look at three different examples here, 1, 2, and 3. In the first situation, our force has some component in the positive x direction, which is the direction of our displacement. And so when we go ahead and we write that our parallel force is equal to F multiplied by cosine of the angle phi, we know that phi is going to be between 0 and 90 degrees, which would give you a positive value for the cosine of the angle. Taking a look at the second setup, where the force is in the backwards direction and the displacement is still in this direction right here, this angle phi is always going to be larger than 90 degrees and also less than 180 degrees, kind of written right here. So when we go ahead and we write the cosine of phi, that is always going to be a negative value. So we're going to end up with work being a negative quantity. The last possible scenario is where the force is 90 degrees from the displacement vector, and we know that the cosine of 90 degrees is going to be equal to 0, and in this particular case, that force will do no work on that box. Something just to state and keep in the back of your head is sometimes you're not necessarily given this angle phi from the positive x-axis. Fairly often you're giving this angle, I'll call it theta here to distinguish it, but you're given that angle right there. It is extremely great practice to go ahead and work everything using phi from the positive x-axis. What I tend to do is I tend to just go ahead and use this angle theta to break up my force into the parallel and perpendicular components, and then just keep in the back of my head that work is going to be negative because force and displacement are in opposite directions. The tractor example is an excellent example of this, where we have a tractor that's pulling a sled with some logs on it, and we can ask ourselves, what is the total work that was done in the system? So first, let's go about drawing all the forces that are on this sled. It's going to have its weight in the downwards direction. It's going to have some normal force right there. the motion is in that direction, so friction is going to, of course, oppose that, and the tractor is pulling upwards at some angle. The book's gone ahead and drawn that a little bit better than I can, so I erased mine. What we can do is we can say how much work was done by the frictional force, and the angle between the frictional force and the displacement is going to be 180. So when we go ahead and we write, our work is equal to our frictional force multiplied by the displacement multiplied by the cosine of the angle between the two. That is going to be 180 degrees. Cosine of 180 is going to be -1. So the work done by the friction force is going to be 3,500 newtons multiplied by 20 meters multiplied by -1. The work done by the frictional force is going to be -70,000 newtons. We can say now what was the work done by the tractor. That's going to be the same thing, force multiplied by the distance multiplied by the cosine of the angle between the tractor's force and the displacement. That's going to be 36.9. We know that the tractor is exerting 5,000 newtons. It pulls the sled by 20 meters. And the cosine, and we're going to have cosine of 36.9. You go ahead and you work that out, and you're going to come out with around 80,000 newtons. Now we can say what was the net work done by the system. It's going to have that's going to be the work done by the tractor, and we're going to subtract, or well, actually we're going to add the work done by friction. That's in the negative direction. So the net work is going to be 80,000 joules minus 70,000 joules. I said newtons earlier. It's going to be joules. Joules is the unit of work, as I mentioned on the second slide. So the work done, the net work done, was going to be 10,000 joules. What the book also does, and follow example 6.2 to convince yourself of what it's doing is correct, is it says, I could also split my tractor's force up into some force of the tractor in the x direction, some force of the tractor in the y direction, and I know in the y direction that all of these forces are perpendicular to my direction of motion. There's my direction of motion right there. So the normal force is going to do no work. The weight is going to do no work. The force of the tractor in the y direction is going to do no work. Now I can go ahead and I could write my net force to be the force of the tractor in the x direction and minus the friction in the y direction, and I can go ahead and I can calculate the net work done. In this case, both of these guys have an angle of 0 degrees with respect to this displacement vector s, and so the cosine would be equal to 1. And we can go ahead and write the net work done. Now that we've talked about what happens when you apply a force to a block, you've done some work to it over some distance. If you've done work to something, you've actually given it something that we're going to call kinetic energy. And the kinetic energy of a particle is written as 1/2 mv squared. I'll note that that v is going to be a scalar. It's not going to have direction associated with it. Kinetic energy is also a scalar. It doesn't have a direction associated with it. It doesn't care if a particle is moving to the left with some velocity or to the right with some velocity. I'll also mention that work does not have a direction associated with it as well. I forgot to mention that in the last slide. But we can actually go ahead and derive this using work is equal to force times distance, and then Newton's laws for kinematics. The book does walk you through where this equation comes from. You can take a look if you'd really like. What it is saying, however, is the kinetic energy. The book writes it with a K. I'm very likely going to write it as a KE to remind myself. Is equal to 1/2 multiplied by the mass of an object multiplied by its velocity squared. And what is going on here is we've done some work to a body. We've applied a force over some distance. That has, given it an acceleration. It has accelerated. It has changed its speed. Therefore, it has changed its kinetic energy. And whether the work was positive or negative, it tells you whether an object is going to increase its kinetic energy or decrease its kinetic energy. Taking a look at the first case, if we have a block that is moving with some velocity over there, and I apply my force like that, and the block is moving to the right, my displacement is to the right, then I know that my work is going to be larger than 0. Therefore, I'm going to increase the kinetic energy with my force. If I take a block that is moving in the same direction and I apply a force to it in that direction, the displacement is going to be in the same direction as the velocity. I know that the work is going to be less than 0. It's going to be negative. What that's going to do is that's going to decrease the kinetic energy of the box. It's going to slow it down. If I look at 1/2 mv squared, you know just kind of intuitively that your velocity is going to get smaller if you apply a force in the opposite direction. So you have decreased your kinetic energy. Last but not least, if you apply a force directly down on the block and assume a perfectly frictionless surface, we know that there is no component of the force that is in the direction of the displacement, so the work done was equal to 0, and in this case the kinetic energy is going to be the same.